Thank you for inviting me and for this nice talk. So actually, my name is Dejan Zagorac. I come from University of Belgrade. I have my own laboratory for theoretical investigation of materials. We have our Center of Excellence located at FeH4 Institute of Nuclear Sciences in Belgrade. And as Professor said, I will talk about atomistic modeling and mechanical properties of iron hydride today. So in principle, since discovery of hydrogen, there is a lot of scientific research done, and there is a lot of applications, of course, of hydrogen, different kind of compounds, etc., etc. And perhaps one of the special interests in materials engineering is the hydrogen embrittlement. And this is also one of the focus of this talk, where we can have iron hydrides, including the FeH4, which I will show you now, which is generally unstable at ambient temperature and pressure and rapidly decompose. And these are some pictures where you can have hydrogen in cars, etc., etc. So in principle, some research started from 2012 in this system with this paper. And actually, you can see in this past work that there is focus. Actually, this slide you don't see it, but the focus actually is on the iron, on hydrogen-rich compounds. And you can see actually on the left side there is FeH4, FeH3, and etc. On the other side are the ones which are dominated by hydrogen. And you can actually see that all of these stable compounds are actually in the pressure range from 100 to 400 gigapascal. So it's extremely high pressure. And there are some structures they found in this paper. Okay. So, but this was followed by another paper, more recent, advances. And actually what they found in the FeH4 system, the system which we are interested today, was that you have an alpha phase structure, and this structure, there is an X-ray here at 80 gigapascal, and then it transforms to around 109 gigapascal to the beta phase, and then even higher pressures up to 241 gigapascal, it transforms to the gamma phase. And these are some structures, how these structures look like. So actually you have on the picture A, you have the gamma phase, the alpha phase. This is the cubic structure. And then on the B, you have the orthorhombic one, the beta phase, which is more stretched. And then the C, you have the gamma phase, which is actually even lower. It's monoclinic in structure. And you can see the coordination of iron by hydrogen. Okay, I also want to point you out to this. This was the, let's say, the hydrogen-rich compounds, but there is also in this paper they point out to iron-rich compound. Like this is the opposite. You have the iron 4H. So we were also interested in this structure, especially because we are interested in what's going on like in materials like industrial steel and everything with the atomistic level, when you can have these traps and what happens with these smaller clusters when they start to create this situation with hydrogen. So actually we found also this paper from recently, like 5 years back, and there is people who managed to make this. There is paper by Paschke, and they created these small clusters of FeH4 on gold one-on-one surface, and actually this is how these clusters look like, and there is the HDM images of this. So actually there's more details if you're interested in this paper. So we are actually on one of this previous conference, we're very proud of this paper. We actually published these models which combine DFT modeling on atomistic level and data mining, and we find different kind of FeH4H system. So this is dominated by iron in these structures. But now, of course, we were interested in vice versa. And for this system, where we now have more, so it's, let's say, the anti, so do we have more hydrogen in the system to investigate? Do we see what happens? And this is basically the first structure prediction method of hydrogen-rich FeH4 system. And there we used combination of data mining and quantum mechanical calculations. For data mining, we used the ICSD database where we have more than 300,000 structures. We used the KDD process, which is selection, pre-processing, transformation, data mining, interpretation, evaluation, and post-processing. And from quantum mechanical calculations, we used Crystal 23 code, which is based on linear combination of atomic orbitals and combined with LDA and GGA functions. This is something from quantum mechanical calculation. This is typical, so this is nothing special. Data mining is more special in this case. And so as a result, usually when theoreticians do this at atomistic level, they create something which is called energy versus volume curves. And this means that you see which structure out of these all calculated predicted structures, which structure is the most stable one. And actually, you can see now that we calculated this first one with the LDA method. You can actually see that the lowest one is the alpha phase. This is the cubic one. And then above in energy, you have the beta and the gamma phase basically competing these two phases. And then repeated these calculations with the GGA functional, and basically you see it's the same trend. So it basically confirms our calculations at the LDA and the GGA level. And the structures we actually found is in principle the same as in previous papers, but previous papers reported only one or two of them. We reported not all three of them, and there is an alpha phase, which is the cubic one. There is the beta phase and the gamma phase, the monoclinic one. And here I actually want to show you the results of this is the unit cell parameter. So the alpha phase crystallizes in the cubic P2 1/3, one space group 198. And there's the sub parameters. And if you compare with one of these papers, you will see that we have actually very good agreement. The beta one is the orthorhombic one, the MMA phase. And again, we compare with the results, we have very good agreement. And the gamma phase is the monoclinic one, P2 1/m in 11 phase. And again, we have very good agreement with only previous theory. So this was not found in experiment. We are just talking about theory. Okay, but now none of these papers, which I'm showing you below, calculated mechanical properties. Normally, they have this type of systems, these type of structures are interested for electronic properties, for superconductivity, for hydrogen storage, etc. But none of them were interested in mechanical properties. So we actually calculated this for each of them. And now you can see actually that for the cubic phase, for 198 phase, this is the most stable one, the SM curves, which I'll show you. This structure, when you calculate the bulk modulus, actually we also did this with three different methods, Boyce-Royce and Hill is the approximate, so we used the Hill. It's 154, something like this. If you this is the standard pressure, 0 gigapascal. And if we go for GGA, it's even less, 116. And now if you increase it to 80 gigapascal, because the prediction from this paper is that the structure is stable at 80 gigapascal, there's a huge increase in bulk modulus, up to 3 times in bulk modulus. And now you see actually there's shear modulus again the same. It's very small and it's comparable to GGA 0. But once we increase to 80 gigapascal, it's not that dramatic, but still it's more than a double. And U modulus, similar story. At standard position, the standard pressure is similar, but when we increase it to 80 gigapascal, it's 3 times, and it's not that dramatic at Poisson ratio. Okay, so now I show you the beta phase, and surprisingly, in this paper, from this very recent paper, these people calculated the, among others, FeH4. So there is different kind of phases, and this was done only in 150 gigapascal because this pressure they found stable, and for that they were interested in electronic, phononic, and superconductive properties. But aside, they put some data on the bulk modulus, on shear modulus, and on Young modulus, and actually Poisson ratios. So we also calculated with different methods and with different pressures. Actually, you can see that for the bulk modulus, we have at 0, so this is not calculated anywhere. it's 216, it's a bit higher than GGA, but this is known from the literature that the GGA is smaller. But when you increase it to 109 in this structure, then it increases dramatically to 608, and it's 157. So it's a bit higher than they got it in their calculation, but still it's approximate. Shear modulus similar, so yeah, the GGA is even much smaller than the LBA, but the increase is not that high, but it's approximate to what the previous calculation got. And if we see the young modulus, it's even more close, and I think the closest comes to the Poisson ratio. So that's really some completely new results and comparable to some theoretical findings in the past. And finally, there's something which is not calculated at all, completely predicted gamma phase, and the calculations with LDA at 0 gigapascal. And then you see, because this structure is stable only up to massively 241 gigapascal, we actually calculated that then in this case, bulk modulus increases 5 times, shear modulus also dramatically increases so 5 times, but actually there is very small increase in Poisson ratio. So I think very interesting mechanical properties. And with this, I would like to summarize and say that we investigated the mechanical properties for the first time of FeH4 compound at standard at extreme high pressures. The FeH4 was computed using combination of data mining and quantum mechanical calculations, and we have 3 novel structures. We created the ESOV curves together with LDA and GGA functionals, and mechanical elastic properties were calculated at DFT level up to 241 gigapascal. And I think this is very important for understanding this complex hydrogen metal interactions and possible hydrogen brittle phenomena in industrial steel. At the end, I would like to say that to thank, of course, my collaborators, Professor Jelena Zagorac, she is from my group, Professor Schön from Max Planck Institute, which we collaborated on this, Professor Milos Djukić, who is also collaborated from University of Belgrade, and Professor Burak from Turkey. Actually, all of these, our collaborators, we applied one big European project for multi-scale modeling. So starting from these small chunks of FeH4 and then going mesoscale, microscale, and then finally to see what's happening in experiment. So we'll see what happened there. And also, okay, Professor Vesna Maksimović, Tamara, Škundrić, Milan, Pejić, and thank you all.